Did you know why cables on cable-stayed bridges are shaped like this? Hello and welcome to my channel. Today we are going to talk about an earthquake-resistant bridge inspired by Vertigo grass and popcorn principles. And who knew that bridge design could be designed by these two unlikely combination of things? So I hope you find it interesting. Talking about none other than the Rion Antirion Bridge in Corinth, Greece. And the issues with this is that there was no bedrock found for over 1,500 feet below the seafloor. By quick calculation, this is about maybe times point, about 500 meters deep below the seafloor. So that's quite deep. So, and if you cannot find rock, then you can imagine how expensive it would be to dig up piles or piers to a level. So I guess it after this at this depth, then it is uneconomical to continue looking for bedrock. So another solution was to be found. Then this is located, of course, in deep waters. The bridge was located in deep waters and also over an active fault. An active fault, of course, this is why we say earthquake. This is why in the title we talked about earthquake resistant bridge, because of course when it is built over an active fault, then we expect earthquakes to hit it often than not. So this needs to be very serious design considerations. And the vertigo grass is usually used to stabilize the banks of rivers, initially grown in India, I think in the rice fields, and it was prone to being inhabited by lots of snakes. So by the principle of stabilizing the river has been used in Africa, I think in Europe, also in India for ages, and also by rice farmers. And so for the same idea was borrowed, so that in the sea, because there was no bedrock, some steel rods were dug, hundreds of them, to stabilize the silt sand, and there was also some clay. And the issue here is that during an earthquake, loose sand and silt liquefies. So basically, when there is shaking, the excessive pore water pressure increases, and then the whole system becomes like a liquid, and then excessive settlements occur and the engineering structures will fail. So this solution of steel rods contained the settlement, but the steel rods really did not touch the bottom because it would be impractical to do that or too expensive. So we just introduced them just like the vertigo grass, not necessarily to touch the bottom, but several of them. Actually, the lengths were, I think, 25 meters, 25 to 30 meters, hundreds of them around the radius upon where the pier was to be put. So this solved the issue of settlement, but we needed the pier was required to rock or to move, because you don't need to firmly hold it on the ground, because that will reduce lots of stresses during rocking and may cause the piers or the structural failure. So if you allow it to rock to slide on top of the ground, reduces the forces transmitted to the structure, and then the structures have a chance to stay. But this causes problems because of the sliding action on the leading edges. The leading edges are prone to what we call bearing capacity failure. So what we're talking about, the bearing capacity failure. So because of the rocking, then the weight of the pier on the leading edges overcomes the soil's ability to resist the forces or the weight, the self-weight of the pier, and this is what you technically can describe as the bearing capacity failure. So one solution is to try to bend up the pier as shown, but this is impractical. I think very difficult to achieve, or impossible, impractical. And even if you're able to do it, then you would introduce other problems, like you can see obviously other stability issues. So that could not happen. Solution: bearing capacity failure. Basically, you just increase the bearing capacity. Of course, there are issues of constructability, but these are things we can deal with. So, because I'm talking about, like, if increasing the bearing capacity, you could do soil improvement or add another layer, like the case was done here, of gravel. But you can imagine at the bottom of the sea, the issues of compaction, how do you construct it? But I think these are challenges that can be dealt with. So, and this is precisely what was done in the case that a layer of gravel was added on top of the pile. So after the not the piles, the rods were put in, then a layer of gravel was deposited and compacted on top, and it was enough to fill, I think, 10 feet, or roughly about 3 meters. And with that, when the 90 diameter meter of the pier could rock or slide over the surface with no issues, and it, according to records, it can slide up to 6 feet, so that is about maybe 0.3 or 2 meters, or 1.8 to 2 meters, or there about 6 feet during an earthquake. So in that way. And then there is the hammock principle. So after you build the pier, then you have to put the deck, right? So obviously there are many other details, but in this case I'm just interested on the interesting engineering principles. Of course, there are other issues of how to put up the pier from the bottom of the sea to the top, but I mean, these are principles that are easily available, but I'm only interested here in highlighting the unique engineering principles used to make the bridge survive or stand under harsh forces of Mother Nature. So the hammock principle was used to isolate the deck from the rocking action of the piers. I tried to explain this. So for example, the hammock shown there tied to the tree, because of the strings shown will separate the rocking action of the hammock from the swaying action of the tree. So the tree can be swayed by the wind, and since we connect the hammock to the tree using some strings, then the hammock can swing independent of the tree. So somehow this system separates the swinging actions of the hammock from the action of the tree. The same principle in the deck. So the deck was attached from the top, kind of suspended, but not attached to the pier directly, to isolate the rocking actions of the two systems. And with this is a closer look. So no connection here, no connection, because typically we lay bridges. This bridge would lie on the pier directly. But in this case, in this system, this is not the case. They are hung as shown here from the pier. So when the bridge rocks, the action of the rocking of the deck is separated from the action of rocking of the pier. And so shown is the rocking action of the earthquake. Now this introduces other issues. For example, if the deck rocks too much, then there's a potential problem that the bridge deck may smash onto the pier at the point shown, and then the pier might break. So this introduces some issue by what we call the viscous dampers. The viscous dampers inside themselves have some oil. These operate like a pump. Maybe I have a better, yes, like a pump. So inside the pumping action, the horizontal forces introduced by the earthquake will be absorbed by the oil inside. So the viscous dampers are attached on both sides. So one side and another side. So the rocking action is absorbed on whether the rocking is on the left or on the right. So the earthquake energy is effectively absorbed. So as already explained, the popcorn principle, you can imagine, I don't know, first of all, how people used to open cans. Actually, I had no idea that the initial cans couldn't be easily opened up like the cans we have today. But the idea is that the cans we have, like the Coke or the Pepsi or the fizzling drinks, are strong enough to protect the drink. Maybe during transportation or storage, the can be shaken or something, but the top is strong enough to protect these actions, but just weak enough that if you want to drink, quench your thirst, then you're able to open it and you take your drink. So that's the idea. So like I was saying, I have no idea how cans used to be opened with no pop-up mechanism. I guess it was a great hassle. So this is the idea, that the deck, and then we can see there the damper shown before, and then the damper, okay, first before that, then we can say, because the bridge has mechanisms to allow it to be able to sway or flexible. It's not good when there are strong winds, because for motorists it would be very uncomfortable across the stretch, and engineers do not design things to fail, or engineers design things to withstand all manner of forces from Mother Nature, and considering all possible environments. So that's the deck, and then the damper has some material, the black one shown. The black material operates like the pop can. It's just strong enough to resist the wind, the strongest wind, but weak enough to be broken by the earthquake. So once it is broken by the earthquake, the damper swings into action, so that it's able to absorb the effects of the energy induced or transferred to the structure by the earthquake. So the implication is that the bridge cannot swing too much in wind, but breaks free conveniently to swing in an earthquake, thereby absorbing the excess energy and protecting the bridge itself. And this action was caught on CCTV camera when the bridge experienced 6.5 magnitude earthquake in June 2008. And it is recorded that structures at least 25 kilometers from the bridge were affected, and maybe a few people died, but the bridge was able to stand. And this is why we say it is a kind of earthquake proof. In the title we say earthquake in quotes, because so many things happen in nature that are very hard to predict, but so far we use data. So fairly, for example, earthquake, we use what we call magnitude, highest magnitude of occurrence in some period. So for example, in some areas, the highest magnitudes that have ever occurred in the Richter scale are 7.5 or 8. So if we use this to design, probably the structure would be safe insofar as the earthquake that will occur will not exceed the maximum, for example 8 or 7.5. So in this case, if the highest magnitude was that it was designed for was, for example, 7.5, at 6.5 it can stand. But if for some reason, because Mother Nature is unpredictable, a higher magnitude, for example, we might not know what can happen. Although all these things are always taken care of in design, such that even if the maximum earthquake occurs, then above what was designed for, then we allow for enough damage but not complete collapse, so that at least lives can be saved. But like I've said, these things are very difficult. Mother Nature is quite difficult to predict how it reacts. But so far, this is what the principles engineers use, and so far, most structures do serve their purposes. So these principles work. And the helical strike, these principles is easy to demonstrate. If, for example, you light a candle and then you turn it off, you can see smoke going up in a swirling manner. And this is very interesting because it is only profound in mild or slow winds or rains. Otherwise, if there is heavy rain or fast wind, then the water or the wind slide fast for this action to happen. But if there is mild or slow wind, then this swirling action can cause serious tests to our structures. For example, there is a case of the Hammock Bridge in USA where it is recorded that fatigue failure was caused. And it was interesting because this only happened during mild or slow winds, but when there was heavy rain or very strong winds, the structure was quite just okay. So these engineers or researchers found out, I forgot the name of the pioneer of this, or the one who found the solution for this. This is called vortex shading. Vortex shading, and this is the reason for this kind of helical shape on cables or on high-rise towers. Next time you see this shape, you know exactly why it is. So this idea is just to protect the structures against vortex shading. The engineering provisions are such that the cost, the anterior, the Rion on one side and anterior, these costs are the costs are moving. Of course, there's a fault. So when there's a fault, then there is potential or relative movement. So there is enough construction joint to allow for 5-meter drift in the coastline, of course, because there is also a fault line there. I think this is not very new principle, so I'm sure it is more familiar than what we've talked about. And then the lightning arresters. I think any tall structure made of steel is quite an attractive site for the billions of electric volts generated by lightning. So it is important to protect the bridge, given that it is in deep waters. Once it is struck by lightning, then it would disrupt the functions of the bridge and probably endanger people's lives. Look out for this helical strike, and you can notice the structures upon it which it is placed, and I'm sure from this video you now know why. So thank the video. Goodbye.